students. Myself, Dr. Pankaj Goel, working as an assistant professor in the EC department at AKGEC Engineering College. Today, we'll discuss a very important topic, enhancement type MOSFETs. As we all know that in VLSI design, there are MOSFETs, which stand for metal oxide semiconductor field effect transistors. These are the basic building block of any VLSI chip. And these MOSFETs have revolutionized the electronic semiconductor industry. So MOSFET transistors are a very essential to semiconductor or electronic industry, and the working principle, to understand the working principle of these MOSFETs is very important. Before we start discussing the topic of today, that is N-channel enhancement type MOSFET, we must know that the MOSFETs are from a family of FETs, in which we have, in FET family, we have JFETs, that is junction FETs, junction field effect transistors. Then we have MOSFETs, and then we have MESFETs, MES-FETs, MESFETs. Now, out of these three type of FETs, MOSFETs are very, very important and used in most of the applications. And if we classify MOSFETs further, then MOSFETs can be classified based on whether there is a physical channel created at the time of fabrication or not. If a channel is created at the time of fabrication, then that kind of MOSFET is known as depletion type MOSFET. Whereas the enhancement type MOSFET is one where a physical channel is not created at the time of fabrication. Rather, in enhancement type MOSFET, channel is induced by external bias, by applying an external voltage across the gate terminal. Also, as the name of the topic today is N-channel enhancement type MOSFET, there are two type of enhancement type MOSFETs. One is N-channel and the other one is P-channel. So depending on the kind of dopants or charge carriers we use. If we are using N-type doping, then it is N-channel MOSFET. If we are using P-channel doping, then it is P-type MOSFET. Okay, so in the figure here we can see it's a physical structure of a N-channel enhancement type MOSFET. Here we can see that the substrate that we have used is a P-type substrate, and the source and drain regions are N-type. Here we can see our substrate is P-type. Substrate is also known as body, and the source and drain regions are N-type. N-type doping is done here. And as we know that in case of MOSFET, we have three main terminals: source, drain, gate. So source terminal is here, drain terminal is here, and then we have a gate terminal. Now, what is special about gate terminal is that it is separated from the wafer, from the semiconductor substrate, by a thin silicon dioxide layer. Here we can see there is a SiO2 layer, this in white color which is visible. It is a thin SiO2 layer which separates the gate terminal from the semiconductor wafer. And then there is a fourth terminal in the MOSFET which is known as substrate or body. body terminal. So this is the physical structure for a N-channel enhancement type MOSFET, in which the substrate is of P-type. Substrate is of P-type, and we can see that here in this type of MOSFET, this channel region, there is no actual doping of N-type material in this channel region. It is all P-type substrate. So there is no physical channel created at the time of construction or fabrication in enhancement type MOSFETs. This is we have to remember. So here we can see that there are two heavily doped N-type regions, which are known as source and drain, and the device structure is completely symmetrical with respect to drain and source. The silicon dioxide layer that is used to create a separation between the gate terminal and the semiconductor, it is typically of the thickness 1 nanometer to 10 nanometer and it acts as an excellent insulator. On the top of this, metal is deposited to form the gate electrode. Here we can see this is metal, this black color layer, this black color layer, these are metals to create a contact for different terminals. Here again we can see this is the metal black color layer, this is metal. Okay, so as I just told you, there is no physical channel, but we know that to make the current flow in a MOSFET, channel must be there. So in enhancement type MOSFET, the channel is created through applied gate voltage. Now we can see here the distance between the drain and source diffusion regions is known as channel length L. It is the distance between the drain and the source diffusion regions. This is channel length. And the lateral extent of the channel is known as channel width W. The lateral extent is known as channel width W. Okay. So here we can see a MOS transistor which has no conducting channel region at zero gate bias is called an enhancement type MOSFET. So this may be the definition for an enhancement type MOSFET, that when the gate bias is zero, then at that time no channel exists between source and drain regions. So that kind of MOSFET is known as enhancement type MOSFET. And vice versa, if when the gate voltage is zero and a channel exists, then that type of MOSFET is known as depletion type MOSFET. So if we are using a P-type substrate and N plus type of source and drain region, then it is N-channel MOSFET. And similarly, if we are using P-type source and drain region, then it is an N-channel. If we are using P-type source and drain regions and N-type substrate, then it is P-channel MOSFET. Another name for MOSFET is insulated gate FET or IGFET. It is insulated gate because there is a oxide layer which is insulating in nature between the gate and the substrate. The abbreviations that we use for the various device terminals are G for the gate, D for the drain, S for the source, and B for the substrate. Now here we can see the cross-sectional view of the N-channel enhancement type MOSFET. Here we know that in case of MOSFET, because of the presence of SiO2 layer, the gate current is essentially zero. So if the gate current is essentially zero, we can see that it is the gate voltage which control the flow of current between source and drain. So the gate voltage is a control variable. So the gate voltage is our control variable which control the flow of current between source and drain regions. Okay, here we can see if the drain and source are kept at the same potential, say ground, and we have applied some positive gate voltage, then what happens? We have applied some positive gate voltage, then what happens? Then here we can see that N-type channel is induced. Here we can see this is the N-type channel is induced between source and drain regions underneath the gate. So we can see a conducting channel is there underneath the gate when we have applied a positive gate voltage at the gate terminal. Now, why it is happening, why the channel is created, is because when we have applied a positive gate voltage, here, then what happens? This positive potential at the gate will repel the holes, from the channel region into the deeper region of the substrate. And as the holes are repelled into the deeper region of the substrate, at the same time, the positive potential at the gate will attract the electrons from the deeper region of the substrate. So, electrons will be attracted and holes will be repelled. And due to this phenomena, a channel is created. So, due to this phenomena, a channel is induced, a N-type channel is induced. And because the channel is of N-type, that is why this is known as N-channel MOSFET. Holes are pushed deeper into the substrate. Okay. Now, when the gate to source voltage is further increased, in that case, surface inversion will be established and a conducting N-type layer will form between the source and drain. Now, as the channel exists between source and drain at a positive gate voltage, now it allows the flow of current between source and drain if there is a potential difference. If there is a potential difference between the source and the drain, then the current will flow through the channel. The minimum value of the gate to source voltage VGS, which is needed to cause the surface inversion, that is to create the conducting channel, is called the threshold voltage VT. If the gate to source voltage is less than VT, then there is no channel exist and no current can flow between source and drain. So if the gate to source voltage is greater than VT, then the channel exists and the current can flow between source and drain, provided there is a potential difference between drain and source. Now, graphically it is shown here that there is a inversion layer and through this inversion layer current can flow. Now, the value of this threshold voltage VT that we are talking about, it can be adjusted by selective doping. The threshold voltage is increased, that is, it is made more positive if we add p-type impurities, and the threshold voltage can be decreased by implanting n-type impurities. So here, if we summarize, if the gate to source voltage is less than VT, no current flow is observed. If the gate voltage is increased and it is greater than VT, then surface inversion is created, and once the surface inversion is created, it is capable of carrying the diode current. Now, let us see the operation with VDS greater than 0. Now we'll see that when the drain to source voltage is greater than 0 and we increase this voltage, then how it affects the current flow between source and drain. As long as VDS is 0, drain current is equal to 0. And if a small drain voltage is applied, then it is observed that the drain current proportional to VDS will flow. Here, because of the presence of inversion layer, the channel forms a continuous current path between source and drain. And this operation mode is called the linear mode or the linear region. Here graphically it has been shown that there is a channel. A channel is present between source and drain for a positive value of VD. For a small positive value of VD, the channel is formed, and so the current will flow between source and drain. Now, what happens when the drain voltage is further increased? The effect of increased drain voltage is that the inversion layer charge and the channel depth start to decrease. Here we can see at this point the channel start to decrease. Here we can see this is the channel. This is the channel width. If we see at the source end, and at the drain end, we can see the channel width is decreasing. And this decrease in channel width is proportional to drain voltage. If the drain voltage is increased, the width of the channel at the drain end, it keep on reducing, and at a certain value, which is known as VD equal to VD saturation, at the drain end, the channel cease to exist. And this is known as pinch off point. As visible, the pinch off point when the channel width at the drain end becomes negligible. Beyond the pinch off point, a depleted surface region forms adjacent to the drain, and this depletion region grows towards the source with the increasing drain voltage. This depletion region grows towards the source, as can be seen. There is no channel in this region as the VD is greater than VD saturation value. The depletion region keep on growing towards the source. So there is no channel and the depletion region is growing. This is the depletion region. You can see this is the depletion region, and this depletion region is moving towards the source as we are increasing the drain voltage. If you compare this depletion region in the previous figure, here we can see this depletion region was less, but as the drain voltage is increased greater than saturation level, depletion region keep on growing and it is moving towards the source. Now, in this case, when the channel width reducing and depletion region is growing, in this case, the current that flows from source to drain is because of the development of high electric field. Now this curve is showing the transfer characteristic of a N-channel MOSFET. Here, when the gate voltage is less than Vt, then there is no current. No current. And as the gate voltage is increased beyond Vt, then current start flowing. Because at gate voltage equal to Vt, channel is formed. A channel is induced between source and drain beneath the gate. Now, the other characteristic, which is the output characteristic. Output characteristic is between drain voltage and drain current. For different values of gate voltage. Here, this is the linear region. As the drain voltage is increased, the current is increasing in the linear region. But at a point when the drain voltage reaches equal to drain VDS saturation level, then the current becomes constant. Here you can see the current becomes constant. And it is happening, the current is becoming constant, it is being saturated, because when the drain voltage is greater than saturation voltage, the channel width cease to exist at the drain end, and the depletion region keep growing towards the source. So the current in that case flows because of the high electric field from the point of pinch off. Sung Mo Kang, Yusuf Leblebisi, CMOS Digital Integrated Circuits Analysis and Design from McGraw Hill, and Cedra Smith, Microelectronic Circuits, Oxford University Press. Thank you.